I hope you enjoyed the Veritasium video there down wherever they were. Maybe Greenwich, England? I'm not sure where they were. It looked like Greenwich to me, but who knows where they were? Maybe, who knows? Anyhow, it doesn't matter. I hope you enjoyed the video and hope you got a qualitative sense for what's going on. I'm going to talk about the situation using this diagram on the right here in just a few minutes. You've got the card with the two slits in it. We're sort of looking at it from above. You know, the two slits he cut in the slide, and then you've got the back of the refrigerator box, the screen here, and he had a little hole cut in the side that you could look into. Also, I'm not going to draw that. That's not important for what we're going to do here. But I'm going to talk more about Young's experiment over here in just a minute. But before I do that, I need to say a few carefully chosen words about an effect, a phenomenon known as diffraction. And I'm going to show it to you both in terms of rays, which we're used to thinking about, and in terms of waves, okay, which we are not so used to thinking about, but which is important for chapter 24. Basically, what diffraction is whenever a wave goes through an opening or around a corner, it spreads out. What does that mean? Well, think about it in terms of rays. Suppose we have a single hole in a card. Okay, so this is sort of a card here, and there's one slit in it. If we shine a light into that slit, so let's think about it in terms of rays here, and all of that light is going left to right, directly through the slit. When that light passes into the other side after going through a small hole like that, it is no longer going in a single direction. So over here, how do I have it worded here? Where'd it go? Yes. The rays in one ray, all the rays, there can be multiple rays, you know. Some of the rays will make it through, some of them won't, but they're all in the same direction. They're all in same direction. But whatever rays make it through the hole, when they get to the other side of the hole, they don't stay moving in the same direction. In other words, the right-hand side of the hole does not look like this. It spreads out. So what you get on this side, seriously, I'm not making this up, is rays in all directions. I am only drawing 5 here. Okay, I'm only drawing 5. But I could draw a ray in any direction. It spreads out in all directions. Okay. Similarly, if you want to think about this in terms of what it looks like in terms of waves, think about being at the ocean. There's a thing called a breakwater. If you've ever been to a port or to a place where a lot of boats dock, oftentimes there's a wall basically that goes around it that breaks the waves from the ocean so that the boats don't get rocked. It's known as a breakwater. Well, that's kind of like our slit here. I mean, the walls here are kind of like that, but there's openings for the boats to go in and out of. And so let me darken this up a little bit. So here's our breakwater here, and there's a little opening for the boat to go through. Looking at it from looking down on it from above, from a bird's eye view. Of course, the analogy is that this is the card and that's the slit. If you think about water waves now, water waves, you can think of the wave fronts as kind of coming in this way. You know, waves on the ocean, right, coming in one after the other, coherent waves coming in one after the other. When those waves get through the hole, they spread out like this. They go in all directions, and so I'm going to draw some rays also, give you an idea. Okay, the waves spread out in all directions. These lines you might think of as the sort of the peaks of the waves. Okay, so troughs are between them. When the wave goes through, the wave, it looks like it comes out of a single point source. It doesn't look like it's coming from it looks like it's coming, let me put it this way, it looks like it's coming from that point right there, from the point where the slit is. Water waves do it, and light waves do it both. This is known as diffraction. Okay. Okay. So that's what happens. It's going to happen here too. All right. So the light is going to enter from the right to from the left to the right here, right? Our laser's over here. The light's all. I'm not going to draw all the rays of light, but you could draw. You could think of the laser light as being, because these slits are very small, very close together, a fraction of a millimeter. So the laser beam itself is larger, even though it looks like a line to us. It's really quite fat compared to this picture here. So the light comes in from the right. I mean, from the left to the right. I'm not going to draw more rays. That could be a little bit confusing for the rest of my drawing. And so what happens is when it goes through, the rays spread out in all directions, right? If it happens in one slit, it'll happen for each of these two slits individually. Okay? So the light's going to go off in all directions. All right? Now remember, what we see on the screen here is a pattern of bright and dark places. Okay? That central maximum I mentioned to you earlier is right there. Central, is this going to stay in? Not quite, but you get the idea. Central max. I'll just write C-E-N-T for the word central. Central maximum. But then you see bright spots as you go out. Above, how does that show up? Yeah, it shows up fine. And below. These bright spots are known as bright fringes, and the dark regions between them are known as dark regions. Okay, so that's the pattern that we get. And what happens with these two waves here, we're going to say in more detail in just a minute. But what I want you to remember is that when the light passes through each one of these slits, on the other side it goes off in all directions. So we have this slit making waves, this slit making waves, and those waves can interfere with each other. This is exactly like in the Veritasium video when dude was down at the pond and he had the two balloons on the sticks and he was bobbing them up and down together. They were coherent sources. The waves had the same wavelength and he was bobbing the two balloons together. Balloon one here, balloon two there. These waves end up interfering with each other. Okay. I want you to notice something here. I meant to bring a meter stick in. I'll try to deal with it without a meter stick. What I want you to notice something is this. The ray, call this slit 1 and call this slit 2. Some ray is going to leave slit 1 and hit the central maximum. And some ray from slit 2 is going to also leave that slit and meet the first ray at the central maximum. Right? These are rays now. They're going to meet at the central maximum. We're going to call this length R1 and that length R2. R1 is the distance the light had to travel from slit 1 to get to the central max. R2 is the distance the light had to travel to get from slit 2 to the central max. There's a very important quantity, okay, that your book our textbook uses the symbol delta for it. And let me see, pink, blue, yellow, here it is. That quantity, okay, it involves this picture here, is known as the path length difference. I can't write. Delta, lowercase delta, is defined as, for this situation here, the absolute value of R2 minus R1, right? Path length difference. R1 is a path length from slit 1 to the central maximum. That's one path length. The second path length is the path length from slit 2 to the central maximum. Their difference is R2 minus R1, and it's defined to be positive. Sign doesn't matter, so we're going to call it positive. In this case, for the central maximum, that path length difference is 0 because length R1, the path length R1 and the path length R2 are equal for that point. Okay. The dotted line is perpendicular to both the card and the screen, and it runs from the point between the two slits. That 0 is for, is this showing up? Yes. Central max. But it is not 0 for any other point on the screen. Okay. Path length difference was 0 for that because R1 and R2 are equal. Next up, I'm going to draw the same diagram, but we're going to pick a point not at the central part, not at the central maximum. We're going to pick a point up here, say, and talk about how R1 and R2 are different and what difference that makes, why that's important for Young's double slit experiment.